Welcome everyone to this presentation, Safe Learning and Control with 𝓛1-Adaptation. First and foremost, I would like to thank the organizers for hosting me as a keynote speaker of this conference. To get started, I have here two animations that have got lots of attention on the media. Here you see AI type of controller or learning-based controller, where, for example, on the left screen, the robot collects the data after every call, uses the data to learn and goes forward. And this video has accrued more than 10 million views on internet. And here is the cubic Rubik that most likely many of you have played with it. A game based on trial and error. It tries to assemble the cubic Rubik, and there have been great success stories with it as well. Having this type of success stories, the learning-based control methods coming from computer science got lots of attention. However, as we work with safety critical systems, such type of approaches are not acceptable. One of the reasons is that when you are in an airplane or in a self-driving car, a crash can be catastrophic and cost you human lives. So what should we do so that to benefit from the availability of data, chip sensors, chip computation on today's platforms, and at the same time, never compromise the system safety? So let's look in a typical learning-based control setup. In a typical learning-based control setup, you have a model learning algorithm that collects the data coming from the sensors. It solves an optimization problem to figure out the controller that's applied as feedback to the system. In such systems, loss of performance and stability guarantees are quite possible when you have uncertainties that have not been accounted in your modeling. You cannot train your model for all possible scenarios, right? Because the accidents like loss of control efficiency or turbulences gas can never be predicted enough well to have a trained controller for those environments. So safety must be built into control architecture as a requirement. So what we do, we add a safety controller that provides your guaranteed safety regardless of the quality of the learning algorithm. And the safety controller will ensure robustness against all type of modeling uncertainties that may appear in your system. The safety controller must provide certificates of performance and robustness that we know will come in the form of transient performance, steady state performance, time delay margin, and disturbance rejection. 𝓛1 adaptive control architecture that was developed by our group over the last 15 years ensures exactly these properties regardless of the uncertainties. This controller has been commercialized for a number of industries, a number of aerospace companies that use that need robust adaptive controllers. And let me skip the names of those. For outside aerospace industries, Evolution Autopilot of Raymarine, drilling applications of Statoil, hydraulic pumps of Caterpillar, and many others. So the typical safe learning and control setup that we are exercising and exploring in our group includes an 𝓛1 adaptive controller as a safety controller that ensures your safety regardless the performance of the learning algorithm. And we have the ability to collect the data through the sensors, and using the computation power on the vehicle, we can figure out how to benefit from the data to have, for example, advanced path planning and more optimality in our performance. The 𝓛1 adaptive controller that was developed by our group over the last 15 years had intensive testing history. So it was first tested on subscale commercial jet at NASA, Airstar within their aviation safety program using their Airstar testbed vehicle. Later it has been applied to a number of other vehicles over the past 15-20 years. Our last flight tests include Learjet and F-16 platforms, where we have already real pilots on the plane, and they are testing for adversarial flight conditions. So just to give you a glimpse of what we're doing, here is a flight test of the Learjet platform. And I won't go through all the details. I'll just turn on the video so you see what's happening. So here is an accidental scenario that has happened in 1967, where likely the pilot remained alive, and the data of that airplane is available today to be loaded on the Learjet test vehicle, which we have access to at Edwards Air Force Base, thanks to one of my former students who is a test pilot instructor there. And as they load the data, we were able to test it for these different adversarial conditions, how our controller will perform. In the current scenario, we have no learning. Let's go and see the first accident, for example, with the data loaded. Without our controller, see what's happening.
I can't even control the airplane. You have the airplane?
Now they repeat the same scenario with our controller on board, and we see how well we perform against the uncertainties.
Okay, task in 3, 2, 1, now. So you can feel there in high frequency, I made some high frequency inputs, excited the roll. Lower frequency, the roll, overshoot, or oscillation tendency is less.
Sounds good.
There's still some there. Pitch, I'm having no issues. Fine tracking and gross tracking are very good in pitch.
All right, and I have maneuver complete.
Now we have an engine loss scenario.
All right, recording on in ready, hack.
Running. Okay, power's coming back. My hands are free. 3, 2, 1, now. Controls fixed. And recover, please. Okay, and recovering. Power's back.
And now without L1, with pilot compensation.
I'm ready to try this now with with a pilot correcting for it. So
Okay, and I'll give it about 1 second of reaction time. I am on conditions.
all right, and then recording on my call. Ready, hack.
On. Okay, power, it'll be left throttle. Okay. In 3, 2, 1, now. 1 potato, and recovery.
And recording off.
Okay, recording off, matching throttles.
Now with our controller, we'll see that the bank angle degradation comes down.
I'm ready for the recording on ready, hack.
On. Okay, left throttle coming back in 3, 2, 1, now. I'm not touching the controls. Nice demonstration. Yeah, check that out. About 3 degrees of left bank. Speeding in the rudder to match. I can feel that. It is descending a little bit, but it's... Yeah, descending a bit, but that would be easy to compensate for. Yeah. Okay. I think you got some good data there.
All right, recording off.
Matching power, recording's coming off.
So with this type of success stories, we look into the further challenges. So we had some media obviously out of it, but say, considering all these other different applications, for example, this is a small robot that can help elderly at home. Let me just run it a little bit. So, for example, deliver a pill for helping elderly, or pick up the fallen fork from the floor, or find the missing glasses, and many other type of in-house applications, like you see, it can bring a small object if the person is just unable to reach out. So we use virtual reality environment for testing people's perception safety, and this small animation from the cartoon movies just reminds us that, for example, a simple application, sponge, they have to shower the lady, and as they try to pick up, the payload is increased. They call their friends for collaboration. Then they try to shower her. Her perception of safety becomes a topic of a subject, subject of interest for us. So while working with these different applications, we encounter also other type of challenges. Last year, Lockheed Martin and MIT put together this animation environment for drone racing competition, where one of our collaborators from Georgia Tech was one of the 9 finalists. And as they were testing their model predictive path integral controller, they were able, for example, to go through 4 gates. But to go through more gates, we were able to help them with L1 adaptive controller. So these new challenges require us to be able to do fast replanning on the go, to have a safe plan, safe controller, and to be able to learn for high performance. As I said, safety is guaranteed by L1 adaptive controller. We use learning to improve the performance. So let's see what we have done. So the autonomy stack, the typical autonomy stack, consists of a planner and a controller. And the planner must conceive trajectories that the controller can execute. So there has to be a two-way communication between the planner and the controller. The typical learning-based control pipeline involves the following steps. We collect the data, we do model learning, we produce control certificates, and with L1 adaptive controller, we have a robust controller around the loop. So it's a bottom-up approach where the foundation is based on control theory, where safety comes as a requirement, and the build-up is based on machine learning, where performance comes as a luxury. The more computation we have, a better ML algorithm we have chosen, a better performance we can achieve. So unified in an architecture that decouples safety from learning is what the focus of our research. Learning does not affect the safety, it only helps to improve the performance. So the building blocks that we look up here will be L1 model predictive path integral controller and Riemannian energy-based L1 adaptive controller for safety, and Bayesian learning of the dynamics would help us to improve the performance. We will look for deep incrementally stabilizing controller to make sure we can extract control certificates. So now let's go step by step through every block. So what do we do with L1 model predictive path integral controller? Having our L1 adaptive control architecture here, so we augment our planner with a model predictive path integral controller that helps us to do faster planning on the fly. That's the beauty of model predictive path integral controller. So as we deployed it in this architecture, let's see how we applied it. So here is what they did without L1, and they go through 4 gates. As they go through 4 gates, they crash because they have to do very fast replanning in the presence of lots of modeling uncertainty. And as they augment it with L1, we'll see how they improve through their passage through more gates. Here it is. We see that without L1, they were failing, and L1 helped them to go through more gates. Basically, we add robustness, and with the help of learning, we can improve the performance. Now, for example, if your robot wants to navigate in narrow spaces, you want to have a safety tube to ensure that, for example, your path planned through the entire time of operation will remain within the safety tube, not to collide with the obstacles. If you plan it a little bit conservatively, you may not be able to find a safe tube because you may collide with these obstacles. So contraction-based L1 adaptive control architecture helps us to plan these tubes. And with the help of L1, we are able to reduce the radius of this tube to make sure we can go through very narrow passages. So, and now we look how to derive quantifiable safety certificates for nonlinear systems, right? So these are the tubes, as I said. With the help of L1 adaptive controller, we are able to tune the radius of these tubes dependent upon our knowledge of uncertainty. And as we combine all these architectures, we have also Bayesian learner that helps to learn the system uncertainties and quantify those in terms of high probability error bounds that we are able to integrate with the L1 adaptive controller for improved performance. So let's look now how we put all these systems together. As we put all of them together, so our combined architecture has a Bayesian learner for learning model uncertainties, a planner that uses the learned model. You see the feedback loop here. The planner uses the learned model to derive control certificate using the contraction-based controller optimization approach. And we augment it with L1 adaptive controller to drive the system, so we are able to tune between the tubes. Here are some numerical examples. As you are trying to navigate through forest, for example, at first you will choose a very thick tube. As you learn better, your tube will become narrow. But as you learn even better, you can choose a more narrow passage and be safe and confident that your safety will be guaranteed. The time of traversing the forest goes down from 27 seconds to 14 seconds, twice more optimal. As we said, safety does not depend upon the learning, but learning can help to improve the performance. And this is what we show here. Here is another example. You have obstacles and you have to navigate in between them. Out of 10 random initial conditions, 8 trajectories collide with the obstacles. We go forward, we choose the L1 adaptive controller that would come with conservative knowledge of uncertainty and give you the safest passage to go from left to right by leaving all the obstacles behind. But if we learn better, if we engage our full architecture, we'll be able to find this narrow, safe passage, and all the trajectories will remain within the narrow tube. Another example, for example, these are all planar agnostic, right? It doesn't matter which planars we choose. For example, a drone that has to leave the square that you see here has 2 exits. At first, it will go through this thick tube. Here are tons of trajectories generated, as you see. Then, as it learns better, it may try to go from here to here, kind of trying to find a shorter path instead of going the long way around. But as it learns better, it will find the most narrow passage and feel safely to go through it. With all these learning model updates, no retuning is required for the L1 adaptive controller, and safety remains completely decoupled from learning. So now as we learn the model, there may be a big question whether the learn model can help us to generate better control certificates in terms of the contraction controller that goes as a baseline controller to provide these tubes. So learning accurate models may not be enough. The accuracy of the learned models is not sufficient to guarantee that the controllers can be synthesized. We need to extract from them controllable models. And here is where we use the deep incrementally stabilizing controller. So what it does, it helps us to extract models that are analytically verified to be incrementally exponentially stable. A projection-based approach is applied here that parameterizes the space of valid candidates using deep neural networks. And because we are already looking into learned models, everything is known there. From these learned models, we're extracting a controllable model. We're talking here about highly nonlinear maps. Extracting this controllable model, for example, it means minimizing the difference between the actual model and the learned model. And using this as your control certificate for the baseline controller that would decide the size of the tube. So the control pipeline, again, if we revisit, would be data, model learning, control certificate learning, and L1 adaptive control augmentation. In this example, just to remind you of the beginning example that we showed that said, when we take these controllers to the real world, they may just not survive because they may be exposed to new data that was not used during their learning. Here we show how we augment, for example, an L1 adaptive controller around a pendulum in a control lab, where the L1 adaptive augmentation stabilizes the pendulum that was trained using RL, reinforcement learning, in offline setting. You bring this reinforcement learning to scenarios where you have uncertainties, where it was for which it was not trained. These uncertainties were not included in training. Reinforcement learning controller crashes, but if it has an L1 adaptive augmentation, it will survive. And here we show a bunch of different uncertainties where L1 adaptive controller is not being tuned. L1 adaptive controller is once designed and it can handle a broad range of uncertainties without any tuning. So a reinforcement learning controller designed and trained in offline environment where the number of scenarios can be brought to the real world in the presence of uncertainties, have L1 augmentation on the top of it, and survive all these uncertainties without loss of the stability. Here we inject disturbances left, right, top, bottom. You will see it doesn't fail, so it doesn't fall. And here are a few real-world problems from our lab where we have used some type of learning, not this particular pipeline. This was a flight test done in 2019 when NASA put forth the Learn to Fly concept to avoid the wind tunnel testing for small consumable UAVs, which are supposed to be cheap and do cost reduction for parcel delivery, for agricultural monitoring and other purposes, where you want really to work with customers that are not ready to pay expensively for a UAV to solve everyday problems. So we have to keep the cost down. The Learn to Fly assumes you take off the vehicle with a random controller like a Ph.D, and then NASA's real-time system identification toolbox has the ability to learn the aerodynamic parameters in the flight, on the go, and we update the model, and model update helps us to update the L1 controller for the performance. So here we deal with already extensions of L1 adaptive controller to switch systems, parameter, linear parameter varying systems. And here are the flight tests from NASA that show how the controller was deployed in real flight. All these videos are available from the YouTube channel of our lab. If you go to our web pages of the university, you will be able to see all these controllers, and they have put scripts, papers. Actually, Learn to Fly was a Ph.D. dissertation in our lab. And summarizing, so this is the other project again funded by NASA to bring L1 adaptive controller along with the perception-based controller of the Georgia Tech lab of Evangelos Theodoros to NASA's flying vehicles. And if we bring the two together to NASA's flying vehicles, so that would be a good demonstration how we integrate methods from L1 adaptive control, track record, literature with perception-based control that Georgia Tech has done for self-driving cars deployed on NASA's flying vehicle. Virtual Sully was another interesting project also launched in our lab. It's still in progress. And here we'll remember the landing on Hudson where the pilot Sullenberger, using his intuition and 42 years of experience, took the rapid decision to save everyone by landing in the middle of Hudson. We would like to see how to conceive such an autopilot that could take advantage of the knowledge acquired in neuroscience, for example, and based on real-time data monitoring, determine the control failures, the new safe mission reconfiguration, path planning, and safe landing site. So doing this three-way adaptation would be ideal if we can mimic, for example, scenarios or use the data from such flight tests to demonstrate the validity of these conjectures. So in conclusion, so we have the L1 adaptive controller that we are able to augment with different planners and different learning algorithms to generate the next generation of autopilots that can safely operate flying technologies or other autonomous technologies, self-driving cars, or be it other applications, where safety would be guaranteed through L1 adaptive controller, and the learning will improve the performance of the optimality. Here are my collaborators that I would like to acknowledge and thank all of them, and my lab. And I would like also to thank all the sponsors that invested in our lab, believed in us, and we were able to go up to these real platforms at Edwards Air Force Base and transition our controller for the benefits of Air Force and society. Thank you all for your attention, and I will look forward to your questions if any.